Hello everyone, I'm Zhimin Wang, a PhD student from Beihang University. The paper I will be presenting today is titled Gaze-Vergence-Controlled See-Through Vision in Augmented Reality. The authors of this work. My talk will be in 5 parts. Firstly, I will be speaking about the background. Superman has the superpower to see the backpack in the locker. This superpower can be called see-through vision, allowing the user to see the occluded objects behind the wall. AR is able to link the real and virtual worlds, which can make this superpower possible. Researchers have made efforts to make see-through vision more natural and realistic. However, the way to interact with see-through vision is less studied. In fact, see-through vision can significantly benefit from interaction control. By intention, the user can turn on or off see-through vision or show it at a different distance. However, we argue that using the common interaction modalities, for example, mid-air click and speech, may not be the optimal way to control see-through vision. This is because when the user wants to see through a wall, he needs to think about the corresponding click gesture or speech command and then execute it. It is not intuitive and requires extra effort to switch the thinking, which will distract the user's attention. Intuitively, when we intend to see through something, we are actually fixing at a new distance, which is physically related to the gaze depth or vergence. Therefore, we propose a novel gaze-vergence-controlled see-through vision in AR. The gaze depth determines whether the see-through vision is triggered. The see-through vision's content is determined by the gaze direction and gaze depth. However, the mainstream AR devices do not support gaze depth estimation. Recent studies using Gaze-Vergence for interaction are mostly in desktop or VR scenarios. To address these issues, our solution contains the following steps. Firstly, we build a gaze tracking model with 2 infrared cameras and assemble it into the Microsoft HoloLens 2. Secondly, we design 2 gaze depth estimation methods, which can be easily adapted to different eye trackers. Thirdly, with our gaze depth estimation algorithm, we propose 2 control models of gaze-vergence and apply them to see-through vision. Specifically, this model utilizes 2 methods to compute gaze depth, which are the 3D line of sight intersection, namely 3D loss eye, and the IPD-based regression. The 3D loss eye is modified from pupil lapse method in 2 ways. Firstly, employ the pupil detection method, PUIST, which has robust performance to reflections or partial occlusion. Secondly, calibrate the hardware in the device and model the kappa angle. The 3D loss eye highly relies on the accuracy of binocular 3D gaze estimation, so it is also important to design a method that is insensitive to the line of sight. We introduce a technique that takes the IPD as input to regress gaze depth. We implement 2 IPD-based methods. Firstly, utilize the physically based IPD in millimeters, namely MIPD, to fit gaze depth. Secondly, use the image-based IPD in pixels, namely PIPD, to regression the depth. We use the exponential function to fit gaze depth. This is our depth calibration thing. Based on our gaze depth computation methods, we design 2 different gaze-vergence-controlled models. One is the stimulus-guided see-through model, and the other is the self-controlled see-through model. The SG see-through model allows users to trigger self-vision by looking at a semi-transparent virtual stimulus behind the ball, which is similar to our viewing habit. The SC see-through model enables the user to freely control Vergence eye movement without the need for stimulus, which is novel and appealing. The window position of see-through vision is calculated as this formula. Please see our paper for more details. We further introduce how to acquire the content of see-through vision from the hidden scene. To make see-through vision more natural and realistic, our solution consists of 3 steps. Firstly, to capture hidden scene, we embed a surveillance camera behind the occluding wall. The camera is first registered to the HoloLens coordinates. Secondly, we further compute the ROI of users in the HoloLens space and map the ROI into the camera space. Finally, we perform a perspective transformation to transform the image of ROI into the user's view in HoloLens. We evaluated the depth accuracy of our proposed methods. That is PIPD, MIPD, 3D loss eye with the Pupil Labs 3D tracker. We make the following observations from these results. Firstly, 3D loss eye achieves the best performance in the range of 0.5 to 2 meters. Secondly, the PIPD outperforms the other methods at the 2 to 6 meters. We combine the 3D loss eye and the PIPD for Gaze-Vergence-Controlled and use the Gaze-Vergence to perform daily indoor interaction within the middle distance, that is 0.5 to 3 meters. We compare the Gaze-Vergence-Controlled techniques with 2 common modalities. For example, mid-ear click technique and speech-based technique. We employ 3 objective metrics and 2 subjective metrics to capture user performance. From the objective evaluation results, we make the following observations. Firstly, we found the SC gaze and the SC gaze were significantly faster than the 2 common modalities. Secondly, users can almost finish the correct operations at the assigned time. Finally, the number of mistakes increased with increasing distance for JVC techniques. The NASA TLX questionnaire demonstrated that the click achieved the highest metal and physical demand than all the other techniques. The speech had a lower metal demand than the SC gaze. There is no significant difference in terms of other task loads. According to the results of the preference ranking questionnaire, the SC gaze is the most preferred by the users. Participants believed that controlling see-through vision is more intuitive and attractive with the JVC techniques than using click and speech. Demonstrate the JVC technique with some example applications.
See through a wall via Gaze-Vergence-Controlled. In this task, the user can see the television through the wall. When the user fixates on the wall, no see-through vision is activated. When the Gaze-Vergence reaches the target depth, the see-through vision is activated. This is simple and consistent with physical laws. The user can also see the moving scene by see-through vision. 3D virtual object display triggered by Gaze-Vergence. In this task, we do not see through but see in front. When the gaze target is on the wall, the user sees a real poster. Then the user controls the gaze vergence to fixate in front of the wall. As a result, a 3D virtual object is shown. This is an intuitive way to trigger different 3D virtual displays. See through multiple occluding objects via Gaze-Vergence control. In this task, the user can see through multiple occluding objects with the vergence control and switch between 4 layers of different depths. When the gaze vergence reaches the depth of each layer, the image of each layer is shown in turn. When the user's gaze depth decreases, the see-through vision switches to the front layers and eventually comes back to the first layer.
It is difficult to discriminate the vergence difference when the distance exceeds 3 meters. Therefore, for long-distance interaction, larger 3 meters, we can use the modality independent of the distance. For example, switch-based technique. In the future, we will design and implement a shared see-through vision between multiple users controlled by gaze vergence. Thank you.